Derive the basic equation of statics for a fluid of constant density and constant acceleration. So I'm going to start with drawing a figure. So we have a container filled with a specific fluid, has a density of rho, and we also have a figure. In this scenario, it's just going to be a cube. And it's going to be at a depth of h. The top of the surface will have a depth of h. The figure itself will have a height of dh, and so the depth from the top of the fluid to the bottom of the figure, that will be just h plus d of h. And this entire figure will have a surface area of A, and we also have gravity acting on the figure. And so in class we had the positive direction pointing upwards, so I'm going to do the same thing, and we'll call this direction z, just like in class. And so since this is a statics problem, we need to form an equation and both sides need to be equal, and in this case we need to find the forces acting up, or acting on the bottom of the surface pointing upwards, and then the forces pointing downwards acting on the top of the surface. So we'll start with the bottom, and so that would be the pressure from h plus dh times that by the surface area will give you the force acting on the bottom of the figure. And then for the top, it would just be the pressure from the pressure at h, top of the figure, times that by a again. We also need to account for the weight, and that would be the density of the fluid times this by gravity, times this by the area of the figure, and then times that by the height of the figure. And so we can cancel out some a's, simplify this a little bit more. H is equal to p of h plus rho g dh. Okay, and so we can subtract p of h on both sides, and we're also going to divide both sides by d of h. Because we need to find a function that we can derive into a statics equation, to a basic statics equation, I should say. And so I'm going to draw a graph to represent this scenario. The x-axis would be the depth we are measuring, so, and we'll just call that z. And then the y-axis, this will be the pressure at whatever depth we're measuring at. And so since the origin is 0 and we are going downwards, the heights will be on the left side of this p-axis. And so we're going down. First height we hit in this scenario will be the top of the surface, so that's h. Next one will be for the bottom of the surface, which is h plus dh. And at h, our pressure would just be p of h, and then for h plus dh, just the pressure at h plus dh. Okay? Closer. So we can add points for these locations. You see it's a downward function or negative function. And so we can now gain a function to derive. That function would be d of p over d of z, going in the negative direction. And since we gained this equation by creating a graph based off of this equation right here, this function is technically equal to rho of g, which we got over here. Now we can actually form an integral. So now let's actually create this integral. So d of p, negative d of p, is equal to rho g, and we can just multiply both sides by dz. And now we place our integrals on both sides. Rho g are both constants, so that actually stays outside of this integral. And now we need to find the bounds. So draw the same figure, container with the fluid with a little box in it. And I'm going to remember that z, or positive, is upwards in this case, and the height is represented as z. And so z, or our height at the surface of the fluid, we're going to set that equal to 0, and then we need to find the height at which it reaches the top of this surface right here. And so z would equal negative h in this case, because since we are traveling downwards, that is going against our rule we said that the positive direction is upwards. So this next bound would be negative h in this case. So our bounds are 0, negative h for the integral of dz. Now we need to find the bounds for d of p. So the pressure at z is equal to 0, and we're also going to set this equal to 0. We're just going to assume that the pressure, the air pressure itself, is just 0, because we're mainly just focused on the fluid. Now we need to find the pressure, or find a way to represent the pressure at the height negative h, and we are going to just use p of h like we did previously in this part right here. And so now we can actually plug those bounds in. Alright, so integrating this, we get p of h minus 0 for this side, and we're also just going to move this negative sign onto this side. So we get negative rho of g, we get to integrate d of z, and so that will equal negative h minus 0. Do a little simplifying. P of h minus 0, that's just P of h, or just the pressure in general. So I'm just going to erase this. We're just going to assume, this is just the pressure overall. And then we have rho g, parentheses, minus h minus 0. Minus 0 just does nothing. So we're technically left with negative rho g times negative h. Negatives cancel out, and we are left with the final expression. P is equal to rho gh.